Thanks a lot, Manfred. I'm just going to share my screen. Okay, so let's see. You should be able to see that. So thank you very much for the invitation to give a kind of guided tour through the Transformers landscape. And if you have any sort of pressing question, I know we have a Q&A session at the end, but if you want to just interrupt, feel free. It's no problem. So just to tell you a little bit about what I'm doing at Hugging Face and to sort of set this sort of motivation for this talk. So I work on two main areas. One aspect is around the open source libraries that Hugging Face develops. So I think many of you are quite familiar with Transformers and the tokenizers libraries. And what I've been working on quite a lot lately is on the Hugging Face Hub library, which I'll show you in a few minutes. And the other side of this, as Manfred mentioned, is on the educational or outreach side of the company. So I'm writing a book with Leandro and Tom on NLP with Transformers. And just yesterday, we launched a Hugging Face course, which is designed for newcomers to NLP and to Transformers in particular, to sort of understand how all the various open source libraries talk to each other and how to get up to speed as quickly as possible. So if you have any young kids or you want to teach your parents about what Transformers really are, you can check out the course. Okay, so let's maybe take a step back and think about sort of how far we've come as a field, because, it was quite surprising to me to realize that Transformers basically turned 4 just a couple of days ago. And 4 years in sort of machine learning research feels like a time dilation in relativity, where it's almost like it feels like a lifetime with the large number of developments that have happened. So everyone knows this very famous paper, which said that you can get away with recurrence and just use self-attention. And then this will give you a very high performing sequence modeling neural network called the transformer. And this produced a sort of Cambrian explosion of many different architectures. And you can see in this sort of subset, very small subset of what we have, that GPT and GPT-2 were the kind of approach from OpenAI to really focus on autoregressive language modeling and push that to its kind of limits with GPT-3, while Google and others pursued sort of masked language modeling with BERT. And then these sort of two main approaches have kind of their strengths and different strengths and weaknesses. And so what you can see is that kind of over time, the number of different models has sort of been growing quite dramatically. And it's quite hard to sort of keep up with all these different papers and also figure out, if I'm a practitioner in industry, which model should I use? Do I just use BERT, or are there better things at my disposal? So the main theme of this talk will be to sort of show you how at Hugging Face we're trying to help make this journey a little easier. So the main ingredients, as I guess you've all seen many times in this conference, behind a transformer is this idea of a transformer block. And one reason why there are so many papers on transformers is because although this architecture is quite simple, there are many variations that you can play with it. So for example, we all sort of know that the original implementation of self-attention has this kind of n squared or order n squared complexity. And so if you want to train for longer sequences, you need to come up with some special tricks. And this has led to, let me see if I get a pointer. So this has led to a lot of research around things like sparse attention or trying to linearize attention. And this drives most of the sort of architectural research. But then what other people have realized is that, it's not just self-attention that is important here. So for example, the choice of activation function in the feed-forward network is important. Maybe we can even drop it entirely. And also the placement of things like layer norm, whether it should be, before the residual connection or after. And so all of these different permutations lead to different types of models or different types of architectures. And the last thing that people have been investigating heavily is the sort of choice of encodings for the positions, because we know that self-attention by itself is kind of agnostic or blind to the order of words or tokens in a sequence. And so we need some way of encoding that information. And there are sort of canonical absolute positions from the original paper, but more recently there are things like rotary embeddings or rotary positional encodings, which try to find a more efficient way of encoding this information. So these are the sort of standard blocks that we need to stack together, kind of like Lego, to build a transformer. But even though the paper says attention is all you need, actually the key thing you also need is to be able to do language modeling. So the two main approaches that we have or converged in the research community for doing this is around masked language modeling. So this is the approach in the BERT paper, where you just randomly mask words in a sequence, and then you ask the model to basically predict the masked tokens. And then the other approach is the autoregressive language modeling from, for example, GPT, GPT-2, and other approaches, where you basically provide kind of like a prompt or some context, and then the model needs to complete this with the next probable token, and then you just keep adding the next word, and then you slowly build up a full sequence of words. So these two kind of ingredients drive much of the research and success behind transformers. And they've kind of led to a sort of modern paradigm of how we think about NLP. So the basic idea is that instead of just training everything from scratch, we can basically take a base transformer architecture, so something like BERT. And then if we have a very large corpus and quite a few dollars in compute, then we can basically do this language modeling and produce a pre-trained language model. And the great advantage of doing this is we kind of only have to do it once. And then once we have this pre-trained language model, we can then adapt it or fine-tune it onto many different downstream tasks. So the advantages of this is that training is usually able to be done on a single GPU. The data set that you need for fine-tuning is typically much smaller than the corpus that was used for pre-training. And this is often easier to reproduce. You don't need to think about distributed training and all the complexity that goes into pre-training. You can more or less just run this in a Colab notebook and see if you can reproduce the results of your colleagues. So we've got this modern paradigm, and it turns out, to some sort of surprise to myself, that it also works for vision. So it turns out that if you take an image, like a picture of this dog, and you can find a way to convert picture into a sequence of tokens, then you can play the exact same game that we play in NLP, where you either do some sort of autoregressive language modeling, trying to predict the next token or the next, say, pixelated token in the sequence, or you can also do masked language modeling, as was done in the ImageGPT paper by OpenAI. And of course, here what's happening is that if you tried to just sort of unravel every single pixel in my high quality or high resolution image, this would be impossible to train. And so what they did here was they used some sort of clustering to kind of aggregate the pixels into different sectors, and then these sectors are the ones that are forming the underlying tokens. And what's become kind of more popular recently is to, instead of trying to do this like clustering by pixels, just to kind of chop an image up into patches, and then we line up these patches as a sequence, and then we feed it through the same kind of ideas that we saw in NLP of using position embeddings and some sort of linear projection in the first layer. Then you just have a standard transformer encoder, some sort of classification head, and then you can do ImageNet at levels comparable to CNNs. So I personally found this to be one of the most surprising applications of transformers. It wasn't obvious to me that this would work for vision, but it does. And the sort of future seems to be of combining these modalities together. So instead of trying to think about how do we model, say, text independently from vision, can we use these together to build sort of interesting tools and insights into sort of how the kind of world works? Because if you think about how we process information, we're not strictly limited to text. And perhaps by combining these modalities, we end up generating a sort of more general form of intelligence. So here, there's some very nice examples by DALL-E from OpenAI, where you basically train jointly on both text and images. And the result is that you can then provide a prompt to the resulting language model, and it will then generate images from that prompt. And here you can see a very sort of unusual thing that I don't think would be in the training set of a baby daikon radish and a tutu walking a dog. And here DALL-E has been able to produce some sort of cartoons that it thinks resemble what you asked for. And similarly for the armchair in the shape of an avocado. So these are kind of like cute and like more fun. But I think the area where we're probably going to see a lot of interest and applications in industry is in the direction of things like multimodal search. So instead of just doing a search in our database with like SQL or even free text, maybe we can start querying through images or a mix of images and text. So we've now been talking about NLP and vision, but I think at this conference, we've also seen applications concerning speech, and transformers are sort of slowly leaking into every domain. So we've now got applications of transformers in biochemistry, which kind of makes sense because you can think about protein sequences, kind of like the sequences of text. And then of course in time series, and more recently in reinforcement learning, which again has this kind of sequential nature to it. So there's kind of a good chance that if your domain involves sequential data, then transformers are coming to it very soon. And I think this is, for me personally, one of the most sort of qualitative differences between transformers and previous breakthroughs we saw in NLP or machine learning, where, for example, things like RNNs and LSTMs, they were quite successful in the domain of text, but applying them to sort of these other things like vision was not, immediately obvious. And I think transformers seem to be able to, or seem to be here to stay, because they could provide this kind of general purpose architecture. Okay, so we can sort of agree that transformers are great, and if you're in research, you're probably pretty happy because you've got tons of questions you can work on, and there's a wide range of directions to pursue. But I come from industry primarily, and here, like, one of the sort of common questions that you would have is like, okay, I just saw this paper released by Google or OpenAI, and it says they get state of the art on some task, and I would like to be able to see if it actually works on my own problems. And it turns out that bridging this divide is not so trivial. So the first thing you might try is you say, oh, maybe I just need to get the code and the weights. And one of the very nice developments in the last few years is that researchers are now providing with their papers implementations on GitHub usually of the paper. And so you might go, okay, cool. I just go to this link and I check out what the model looks like and what the weights are. But this has its own challenges. So the first one is that you sort of have to basically scrape the archive or GitHub, trying to find the model that sort of matches the task that you're interested in, or the domain you're interested in. And this is just a very tiny subset of different models that are available. And as we saw that transformers are going into new domains, this sort of web is just going to grow larger and larger. So it's kind of hard to figure out where do I start. And the other thing is that every implementation kind of has its own idiosyncratic API. Maybe it uses Python 2, maybe it has no documentation. And this leads to a whole range of kind of reproducibility issues. So if you've ever tried to sort of re-implement your own transformer kind of yourself, just using the paper or just using the code that's available, you may have experienced that it's not so easy to get the exact same results, because there's all sorts of tricks that are not mentioned either directly in the paper or in the code itself. So we've kind of got this wild west of models and papers all over GitHub. And the question is, can we do better? So at Hugging Face, the vision and the mission is to kind of unify this landscape in a sort of centralized hub. And here in the sort of landing page, we provide different sort of hubs where you can search for different models, data sets, and other resources. And the sort of underlying philosophy behind this is that all of this state-of-the-art research should be easily available to developers and to just the general community. And so to do that, you not only have to provide access to models, but you also have to provide the tools that enable people to be productive. And as you are familiar, we have a range of open source libraries to help people be productive, both in research and industry. So there's the Transformers library, there's the Datasets library, and the Tokenizers library. These form the kind of central pipeline for stitching together all the things you need to train a transformer. And more recently, we've launched a library called Accelerate, which I'll briefly mention, which is to help you do distributed training in a much simpler way. And there's also the Hugging Face Hub library, which was just launched a few weeks ago, which basically provides you with an interface to the whole Hugging Face Hub, which you can basically query programmatically. So what I thought I would do is kind of walk you through the ecosystem kind of end to end. So imagine that I'm trying to solve some task for my job, and maybe I work at, I don't know, Digitech, and I've got all these different products, and people are asking questions about my products. And I would like to be able to sort of automatically respond to these questions without relying on, the community or my staff to do this. So the first thing I might think is like, okay, this kind of sounds like a question answering task. So what I would do is I go, okay, I need to find a model that is like suitable for this task. So the first thing I do is I go to the model hub. And on the model hub, we have around 15,000 models. So quite a lot of models to navigate through. But we provide various filters that let you kind of drill down into the sort of subset of models that are most relevant for what you're interested in. So for example, here we can have a breakdown in terms of tasks. And so we might select, for example, question answering. And we also support primarily three main backends. So perhaps you code in TensorFlow, so then you can find which models are available in TensorFlow, PyTorch. And we also provide scripts that make these interoperable between them. And there's also more recently JAX, which has been implemented. And then one thing that I always found working in Switzerland is like, most of the sort of research that's published typically is English or trained on English corpora. And so one thing that you typically care about is finding, for example, models that are sort of specifically trained on German. And so here we might filter this question answering set of models for things like maybe the Swiss languages of French, German, and Italian. So now we get some subset of models, and we say pick one that we think is suitable. And then the next thing is to take that model and then load it into the tokenizers and transformers libraries. So the API for both these libraries has been designed to be more or less as simple as possible. So typically just a few lines of code. And generally you just need to provide a checkpoint that specifies which model you're interested in. And then this will provide you with both the tokenizer and the model, and it will download all the weights and all of the configuration from the hub, so that then you can immediately go ahead and start training. And there are different classes for different types of tasks. So here, this particular task is, say, masked language modeling, but in the case that we were talking about before, this would be something for question answering. And then this will automatically put on the head on top of the pre-trained model that is suitable for that task. So currently in the Transformers library, we have over 50 different model architectures, and these are used by more than 5,000 companies. And the sort of driving principle behind the library is just to have a simple API across all the architectures. And this is designed to tackle that problem I mentioned where, just publishing your code on GitHub is like step zero, but the real productivity comes when I can basically switch between models just by switching, the checkpoint. And that's what the libraries are designed to do. So having a model and having a pre-trained model is great, but of course we need data. And this brings me to this other aspect of the Hugging Face Hub, which is to do with data sets. So, when I was working as a data scientist in industry, the sort of common thing you would try to start with is, of course, your own in-domain data. But most of the time, you start a project and your clients would say, well, we've got this data, but it's not labeled. Or, we've only got 100 samples or something like this. And so a very effective way to just test whether the problem that you're interested in solving is even soluble is, of course, to first build a baseline, because, we all build baselines, right? And then once you've got that, to think about, okay, if I wanted to improve this with transformers, maybe there's a data set available publicly that I can kind of bootstrap on top of. And so to enable this, we provide on the hub over 1,500 different data sets. And these are all provided by the community, but also include many popular benchmarks, for example, Squad, Sentiment 140, and so on. And again, these are arranged in terms of task and also language and the size of the data set and so on. And so this allows you to sort of quickly drill down into finding a data set that is suitable for your task. And as I mentioned, we've got over 450 languages, over 1,000 data sets. And the driving principle behind the library is very similar to transformers. So you want to be able to provide developers with the ability to just load any of these data sets with just one line of code. And the other thing that was quite a challenge, at least for me personally, before this library was available, is that if you ever have to process very large corpora, you typically run into sort of RAM limitations. So, imagine you've got I don't know, a 4 GB corpus that you want to sort of pre-train on. Trying to tokenize this data set without any sort of special tools is quite a pain. You have to do things like multiprocessing and so on. And data sets uses Apache Arrow under the hood to basically ensure that everything is done without sort of maxing out the RAM in your laptop. And this also enables very fast sort of iterations in your sort of pre-processing and querying. Cool. So let's suppose we've found a model, we've got a data set, we've maybe trained on this or fine-tuned on this data set, and we're sort of happy with the results. And now we want to share it with either our collaborators, or perhaps we just want to share it with the community so other people can build on top of it. And so this final step in the workflow is to upload it to the hub. And this is where the Hugging Face Hub library comes in. So much of this pushing to the hub is abstracted away in the Transformers library. But if you're interested, you can actually interact with the whole hub programmatically by basically using this Hugging Face API. So for example, if I'm doing something that's a little bit custom and maybe not in the Transformers library, I can have my own sort of PyTorch module or PyTorch model. And then I just include a model hub mixin. And then once I've trained this, I can just say push to hub. And then this will automatically wrap the state dictionary, the weights, all the config, all the things that are often a pain to keep track of. It will wrap them up and push them to your organization on the hub with some tag and version. And then once you have this, you can just say to your colleague, hey, you can now interact with my model and just say, from pre-trained, blah, and then the model is available to anyone who has access to your organization. And we've found from our user feedback, this is a very powerful way of iterating in teams, because you no longer have to think about, okay, do I store my weights in my Git repo, or do I send it by email? Do I zip it up? This is all basically handled now through just a few lines of code. And the other thing that's been happening in the last few months is a push beyond the Transformers ecosystem. So we're now working closely with Allen NLP and Spacey and the amazing TIM library for computer vision to basically provide these interfaces so that you can push to the hub from your kind of favorite framework. So most of the time, maybe you don't need a transformer, maybe you just want to use some sort of Spacey models, and these are now soon going to be available as well in the hub. And then, if you're a researcher, perhaps you stop at that point. But in industry, the sort of thing that really drives the value at the end of the day is being able to sort of serve predictions. And this is where Hugging Face provides its own Inference API. So you sort of don't have to write your own Flask apps or Fast API apps. And it kind of looks like this. So basically you have a model that you've trained. So in this case, Distilbert base uncased. And this is now a language model that just is going to fill this mask token. And this Inference API allows you to basically interact kind of with your model in real time and see what it looks like, whether the outputs make sense. And you can do this for more complicated things like named entity recognition. And if you're a company that you want to have an SLA, or you want to have be able to basically query this endpoint, you know, with a large number of requests, then there are various pricing options available. Okay, so that was more or less a whirlwind tour through the hub, starting from a question about a model, getting a data set, and pushing it back after training. But I didn't really talk about, you know, the training loop. So let's have a look at sort of 3 different ways you can train models in Hugging Face. So the most common way is to use the trainer. And here's like a sort of mountain of code. It looks like it, but it's just actually three classes. The first thing you need is a model, and then you need to provide some training arguments. These are basically your hyperparameters, the number of epochs, how big your batch size is, and so forth. And then there's a trainer class where you provide a model, the training arguments, and then the data sets that you wish to train and evaluate on. And then once you've trained it, you can just do push to hub, and this will then automatically wrap the model, the tokenizer, and push to the hub into your account. And this is, I think, the most common way probably people are interacting with the Transformers library. But just recently, one sec. Yep. Just recently, Sylvain Guga at Hugging Face released the Accelerate library, which is designed for people who want to go deeper and sort of really interact closely with the training loop, but they don't want to care about the whole device placement and thinking about, you know, what do I need to do if I want to train on 4 GPUs or 1 GPU or a TPU, or all these kind of annoying infrastructure problems you have to configure if you do this yourself. And there's basically just 5 lines of code that you need to add to your training loop to use this with Accelerate. The first one is you define essentially an object called an accelerator. This will automatically work out what kind of hardware your model or your script is running on. And this will then automatically get the device. And then you just need to prepare the model, the optimizer, and the data using this accelerator object, and then just call backward instead of the standard PyTorch loss backward. And this will automatically take care of all of the nitty-gritty of like, how do I compute losses in distributed settings? And you don't have to really worry about all the boilerplate that goes associated with that. So this gives you a lot of control about the training loop and the devices. And here's an example where you can sort of, if you want to really change the device specifically for, like, you know, sources and targets, you just do this by just specifying that you've got a transformer, and then again, the accelerated backward loss will automatically take care of it. So if you're doing very large scale training or you're working with TPUs, you might want to check this out. It also works in Colab, so you can get kind of the best of Colab's like free TPUs with just a few lines of code. And at the moment, we currently support training and evaluation and different devices like CPUs, GPUs, mixed precision. And Sylvain and Stas are working heavily on integrating things like deep speed, which allow you to do crazy stuff like train, you know, 11 billion parameter models on a single GPU. And if you have other kind of frameworks that you would like to be integrated, just open the issue on Github. So everything I've told you so far is heavily geared towards developers and researchers. So the idea is, like, if you know how to code, you know PyTorch or TensorFlow, you can sort of quickly get up to speed and train your own models. But one sort of common request from the community was to provide a kind of much simpler interface. If you just want to quickly find out, you know, is my problem sort of amenable to transformers, but without going through all the hassle of training multiple models with lots of scripts. So we have a sort of new product or a new, say, library called AutoML. And the idea here is to provide a kind of low code environment. So you specify essentially a project and you provide some data and you say, okay, these are the columns I want to train on. And then you just say train, and this will launch a job in the backend, which will basically do some clever hyperparameter optimization, model selection to find a set of models that achieve the best kind of performance as you define across, you know, different data sets if you wish. And then at the end of this model will then be basically exposed on the hub, and then you can query it using the Inference API. And so this is perhaps if you're more of like a software engineer and you don't really want to spend all this time learning what transformers really are, this is a sort of simple way to get started and find out if it would make sense for your project. Okay, let's see, what do we have next? Okay, so that sort of wraps up like the guide through the Hugging Face ecosystem. But the other thing that Hugging Face is heavily invested in is research and science in general. And I'd like to sort of spend these last 10 minutes or so talking to you a little bit about something called the BigScience project. And this project was launched by Tom Wolfe and others in the French research community. And if you're interested, you can go to this URL. And the basic idea behind BigScience is to basically conduct a sort of 1 year long research project or workshop studying extremely large multilingual data sets and large language models. And the sort of inspiration for this comes by analogy with the Large Hadron Collider at CERN. So the LHC, over its history, has involved over 10,000 researchers spanning over 100 countries. And this kind of collective sort of scientific collaboration has led to the discovery of things like the Higgs boson, but also many other hadrons, and the publication of several thousand papers. And this kind of like large-scale collaboration is also common in other fields like epidemiology, space research, fusion, so on and so forth. And the sort of pattern you see is you're trying to tackle some very sort of fundamental questions in the field, but no single research lab or even company has the resources to do that. And so the basic question behind BigScience is whether it's possible and it makes sense to start creating an open source or an open research collaboration that is large and diverse like the LHC, but targeted for AI and NLP. So the motivation to do this comes from several fronts. So the sort of first observation is that, over time, we're seeing that language models are getting trained on ever larger data sets and also with a much larger number of parameters. And so you can see that, for example, this is already out of date. We have things like switch transformer, which have over 1 trillion parameters. But you can see, a dramatic growth in the scale of the models in terms of the parameters compared to, just a few years ago. Talking over 1000x, which is, pretty dramatic growth in scale. And the sort of driving force behind this has been the observation from companies like OpenAI and Google and Facebook that as you scale the models with the number of parameters, you end up observing some pretty impressive zero-shot and few-shot capabilities. And this opens up sort of a whole range of questions about, do we need to even keep thinking about this paradigm of fine-tuning? Maybe we just need to train an enormous language model, and then with some clever prompting, we'll be able to kind of have a very sort of intelligent system in some sense. So industry is kind of going ahead and doing its thing in this way, but this isn't really available to the sort of common or average researcher or practitioner. And there's a couple of reasons why. So the one is that these models are typically not designed as general research tools. So more often than not, they're either commercialized or they're exposed just through, say, the weights of the code bases, and then you don't really have a sort of handle on the data or maybe the hyperparameters or the tuning or the training. And the other thing is that most of the sort of academic researchers involved in these projects, they have their own things they need to do. So once they've kind of done the paper, it's time to move on and build new things. So if you want to sort of interact or continue interacting with the sort of research, it's hard to get direct contact. And the other aspect is there's a sort of lack of some diversity in the teams that build this. So typically you're looking at maybe 10 to 20 people involved in building these language models. And this kind of lack of diversity perhaps changes or limits the number of or the type of questions you might ask from a research perspective. So that's on the research side. And then the other thing is that even though we know that companies like Google offset, all of their compute, so they're kind of carbon neutral, this isn't sort of always clear in other contexts. And so we also see that like this kind of arms race towards training very large language models potentially is leading to like sort of redundancy and sort of energy requirements. And it'd be nice if we could kind of do this perhaps just a few times, but also be able to interact and ask all the kind of research questions we would like from this, instead of just comparing who's got the bigger model. And then the sort of last one, which is also quite important, are like the ethical and societal questions around these language models. So it's well known that essentially if you train, say, GPT-2 on Reddit, you're likely to pick up many of the biases that are present in Reddit. And this includes things like racism and sexism. And a lot of the time, the kind of questions that, the research community is able to ask, or even the industry leaders ask, is often after the fact. So, we all know of these like kind of embarrassing examples where a company releases like something like, a chatbot, and then it turns out this chatbot quickly becomes, very xenophobic. So it'd be nice if we could kind of ask these questions in advance as a research community without sort of having to wait or rely on just a small number of companies. Grace. So that's the motivation. And fortunately, there are alternatives to just using Google GPUs. So it turns out that in France, there's a supercomputer called Junze. And this supercomputer has roughly the sort of performance of the peak performance of around 28 petaflops per second. And it's roughly equivalent to having a few thousand NVIDIA V100 GPUs. And here's a sort of nitty-gritty breakdown of the different types of GPUs and processors that are running on the supercomputer. And so when Tom was thinking about this idea of putting forward a large collaboration, he got in touch with the Junze supercomputer team, and they were very open to this idea of trying to see if we can train a very large language model. And so once that sort of initial contact was made, the science team at Hugging Face and many other members of the French academic research communities, they joined in to sort of refine the goals and scope of the project. And a grant for 5 million GPU hours has sort of just been approved just around 2 months ago. And there's now over 500 people involved all over the world. And the project was kicked off on the 28th of April and is now open to anyone who wants to join. So the kind of research questions that are being discussed at the moment is what I was discussing before about. We've seen that from things like GPT-3, that these large language models and large data sets, they kind of have some emergent behavior in the few shot and zero shot setting. And then the question is like, is this really like language understanding, or is it just some sort of like statistical or correlation that is being picked up in the language? And what is the kind of like relationship between things like sort of tasks and benchmarks, and whether things like prompting or prompt engineering are sufficient to have some sort of general model. And then of course, all these questions around bias and fairness and environmental impact. So these are sort of the research questions that are being asked in advance and being refined before the language model is trained. And what's quite interesting here is it's kind of a little bit closer to what I remember in physics, where you would sort of have some, let's say, observational anomaly, and then you would try to find answers to those questions. And then you sort of wouldn't know in advance if your sort of theory would be correct. And so you would have to sort of do some calculations and then check, does it actually predict the world as we see it? And this has a sort of similar flavor of trying to ask questions in advance and then see if we can test these hypotheses. So if you're interested in participating, there's 4 main sort of roles. One is at the level of being like a sort of general advisor. And there's a steering committee which kind of is driving the sort of whole project. There are several working groups, typically broken down in terms of modeling, the data set, curation and creation, visualization, evaluation, and also the sort of societal impacts. So you can check out the website to see if there's a working group you're interested in. And then you can also create your own working groups and then chair them. If there's a particular thing you think is missing that is important, then this can be pitched. And if the committee approves, then you can create your own working group. And then the final one is sort of the more general role of being a workshop attendant. And we're planning in the sort of near future to have some live events, potentially some community events. And here you can contribute at the level of, it's up to you basically. You can just join the discussions, or you can write code, or so on and so forth. And there are going to be various sort of research articles generated from this collaboration. So if you're a sort of early stage researcher and you would like to do something that is quite, a moonshot project, this would be an exciting way to join. So with that, that's my 42 minutes. Maybe we can go to some questions. Thank you for listening.
Thank you very much for this outstanding keynote, Louis. I missed to mention in my introduction that you worked as a theoretical particle physicist on dark matter and the universe, and you were involved in the Large Hadron Collider at CERN. Therefore, it's only logical that you try to introduce a large language model collider now, and hopefully that's going to fly.
True, I should mention this was actually Tom's idea, and he's also a physicist too. So I think there's like an invasion of physicists in machine learning, and probably. But
he's also a lawyer, isn't he?
Yes, exactly. He's many different hats.
Okay. Yeah. Are there any questions from the audience?
That's klar.
There is a Konstantin asking if there are banks for transformers owned for data set.
I guess this is the idea of like hubs, right?
So, Louis, thank you very much for the presentation. I saw that you presented banks of data sets and transformers.
Probably we can't hear you, Konstantin.
Is the sound off?
It's quiet.
How about that?
That's much better.
Right, so the question is, so we have the banks of data, we have the banks of models. Is there a bank of use cases, list of applications?
Yes, so we're actually working on this, and this is something that I'm heavily involved in. So there's two sides of it. One is to provide sort of like guidance on which tasks are suitable, and to provide some sort of curated list of models that you can use for those tasks. And the other side is to figure out how can you do large scale evaluation across the whole hub. So we've got 15,000 models, 1,000 data sets. Can we evaluate all of them and then provide users with the idea that, okay, my use case is, say, text classification. Can I find the best performing model on this data set for these metrics? And so this is, let's say, work in progress, but it's something that we're definitely trying to solve. And I mean, if you have perhaps an example of what you're trying to solve, that might be, just reach out to me, or just leave a message on the forums, and you can help guide development. So I think Andre has a comment that the pipelines are prototypes. Yeah, so that's right. So the pipelines are sort of like, let's say, tasks. So we have a different pipeline which bundles together the, let's say, for text classification, all the steps you need to take some raw text and provide a label or a predicted label. But we find that this still requires some sort of technical know-how. And so one aspect of what we're doing is to sort of bridge that gap of, like, for example, if I'm a product manager, maybe I'm not super knowledgeable about all the technical names of things. But the other thing that pipelines don't quite offer at the moment is a sort of insight into how well the model performs. And that's the thing I was mentioning before. Yeah, good point. Mohammed says, can we get the presentation? Sure, I'll be sending this to the organizers today. So whenever they release it, it's available. So maybe I can ask a question. I don't know.
Yes, sure.
So if there is one thing you could change, or what is like the one most frustrating thing that you find with, say, transformers, the library, or the ecosystem? Does anyone want to tell me?
Hi, Louis. Actually, I am a big fan of Hugging Face because I use a lot of Transformers models on it. But recently, I found that the model with no limited sequence length is very little on the Hugging Face community. So did Hugging Face do Hugging Face have any plan for building some Transformers models for those extremely long sequence input data?
Yeah, so the way that like, let's say the choice to integrate a model often works is there's like some shortlist and you can suggest a model and the team might be able to implement it. But one thing that recently was done to sort of tackle this kind of question is to integrate, for example, Big Bird, which has this sort of long range component to it. And this was done by kind of partnering with a member from the community. And so the idea is that there's I'll put a link in my slides at the end, which if you want to work with one of the Hugging Face engineers on implementing your own model, like say your own published model from say Facebook or whatever, then you can do that. And this might be one way of addressing this gap. But coming to the question of specifically long range transformers, I think this is sort of part of the roadmap, but you know, we're only like, I think in the Transformers team, it's like 5 to 10 people. So it takes time.
Okay, thank you.
Cool, thanks Andre.
Konstantin, do you want to ask something?
If there's no one else asking a question, I'll probably use the opportunity.
Again, we can't hear you.
Yes, if no one else is asking the question, I'll try to use the opportunity. Louis, I work in the area of localization, and many of the corporate localization people are looking also into copywriting. Mm-hmm. And of course, this year there's this big information, the news splash about GPT-3, mm-hmm. and quite a few companies like CopyAI, Copysmith have just got funding in that area, and they're all the rage. However, the corporate localization people who I talk with on a daily basis, they want to know if they can productize this, take advantage of this somehow. Basically, they want to replicate what is going on with machine translation, where you have the raw output post-edited by a human in the loop approach. Mm-hmm. And it's less expensive than translating from scratch. So basically, they attack the cost. So there is a theory that the GPT-3 models will be used for corporate copy, corporate writing, electronic copywriter with the same post-editing model. However, there must be some kind of way how this could be fine-tuned and tailored to the enterprise with their specific language, specific requirements. How do you see this market evolving?
It's a super tough question. So I think the general rule is you shouldn't predict the future, especially if you're doing machine learning. But let me think. So, okay, so maybe I'll give you a very personal biased answer based on my experience of working in Switzerland. So most of the time when I was working in startups or companies, we couldn't even use like GPUs because Google Cloud was in like, you know, Germany, and, you know, everything had to be in Switzerland. So one side of this is that my sort of feeling is that many like mid-sized to large companies in Europe are quite conservative about both sharing their data with a US company like OpenAI, but also, you know, thinking about the compute, like where is the compute done? So perhaps there's like two sides of it. In the US, where things are wild, I guess the field will evolve as fast as OpenAI is able to sell and convince people that there's value in taking this approach. To be totally honest, I don't have a good answer to your question. I don't really know what the future of this kind of interaction would look like. But one thing I could mention that might be interesting is there's a sort of independent research group called Eleuther AI, and they are trying to replicate GPT-3 themselves. And they've already produced a model called GPT Neo J, or GPT-J, I forget, 6 billion or something. So it's basically close to one of the sort of smaller models that OpenAI sort of provides. And they're trying to go the full way to like 175 billion parameters and just release it. I mean, they think the future should be completely, free. So that's one way I could imagine things would evolve, where people start just building their own thing that way and bypass OpenAI. But the challenge always is, right, how do you do inference on these humongous models? And so you typically need, like, you can't put all this model in one GPU. And so the infrastructure question presumably will have to be solved by some companies if they want to do that. And then the other side of this is one artifact from this BigScience project is also to provide a large language model and to make that available in some capacity. It's not clear exactly what they'll be like. So if you keep an eye on both these projects, you might be able to see ways to sort of test these sort of ideas freely.
Maybe may I have also ask a short question?
Sure.
Thank you for your nice presentation. I already worked with also Hugging Face and like some variation of Hugging Face like Flare and others. Just want to know your idea about automatic deep learning. I mean, the new method that actually the people are working with this configuration file, and so you only need to kind of set up this configuration file and change your data set, and then it's done. What do you think about this? I mean, I'm not sure that can I call it a new era in deep learning, but for me as a user, it's kind of like this. I want to know that in which way that we can have like more interpretable approach, or is it at all necessary, or what do you think actually? I mean, you mentioned that we shouldn't predict the future, but I mean, I want to know your idea as one of the developer of the Hugging Face.
Sure. So before I was at Hugging Face, I actually worked on at a startup doing AutoML, and it wasn't really AutoML. It was more about like no code ML. So how do you provide a sort of interface for domain experts to train their own models? And this turned out to be way harder than I thought. And one reason it's quite hard, I think, to automate a lot of this cycle is that you really need to look at the data and look at the predictions of the model and make some sort of decisions that often depend on the domain. And I'm not sure how we break out of this human in the loop process and just say, here's a data set, here's a model, click, boom, go home, cash in my paycheck. I personally think, and my experience having worked on sort of very messy industrial projects is that it's never as easy as like, dot fit, dot predict. So I'm personally quite skeptical about AutoML in this setting of like truly automated end-to-end solutions. But I could also imagine that we start having more like sort of human in the loop frameworks that let us kind of abstract away some of this boilerplate, because even though transformers is a super nice like API in my perspective, I still have to write code. And it would be kind of cool if I could just talk to my computer and say, hey, I want to do these experiments. Can you sort of do them? and
also reproducible somehow. Like for example, SAC recently used this configuration file, which is, I mean, it's kind of communicatable and reproducible somehow. I mean, it has some disadvantage, of course, but also some advantage. Thank you for your answer.
Thanks for the question.
Maybe I may ask you a more technical question, because there is an issue in transformers I never really understood. Mm-hmm. That's about the formulation of the positional encoding, mm-hmm. Especially because in the Vajwani paper, description differs from their implementation. I never understood how they figure out how to do that.
Ah, okay. Well, that's a deeper question. I mean, maybe you have to ask, Vashwani, where they got the idea from. But is your question sort of the origin of the sine and cosine approach, or is it more about like why we need to do this?
Yeah, how they get to this formulation.
Okay, so the simple answer is I don't know like the story behind that, except I have a vague memory that it was one of the software engineers. It was kind of like let's say a hack. Like we need to figure out how we can inject some positional information, and we don't want to learn it from scratch. And the idea that like in a sequence, you might have some sort of frequencies of like where words appear in certain orders. Maybe the guy was an electrical engineer, and I don't know. But I honestly don't know the answer to that question. Like,
so it's just trial and error.
Well, plus being clever, as in the idea is that like with these positional encodings, I mean, since that paper, people have realized that there are like more sort of, let's say, sophisticated ways we can integrate some notion of like what it means for words to appear in an order. But for the original implementation, I'll try to find out. I don't know the history of that. I don't think it was random. I think it was probably a lot of clever thinking about how do you sort of shortcut just learning embeddings from scratch, because you could do that, right? You could just have a way of just learning the positions just with brute force.
Okay. Are there any other questions?
Yes, just maybe one quick one about, or not so quick one, but perhaps what your or also Hugging Face take is on, let's say, a bit of the future in terms of an emerging topic, I think, is multimodal systems or multimodal transformers, like combining vision and language models to sort of tackle the age-old symbol grounding problem.
Mm-hmm.
Because linguistically speaking, what we're doing with language models is still based on the distributional hypothesis of semantics. So we don't really have any solution to the symbol grounding problem. And I don't know, maybe you have some thoughts on that or plans to go into this direction.
Yeah, so I know that Tom Wolfe is really bullish on multimodal. So in the sense that he thinks this is really like a key step to the future, and for the reasons I think you mentioned. And from the perspective of the Transformers team, we've already integrated things like Clip into the library, and the library is expanding beyond NLP now. So just a few weeks ago, the release was made for Vision and these multimodal setups. And like one thing that I would say is that from a Hugging Face perspective, like at the moment, we don't really have like the sort of computational resources of Google and OpenAI. So we don't say generate our own models, but we focus on making them accessible. So as this field evolves, they will become available. And the other side is, of course, focusing on the efficiency thing. So like that's more like Hugging Face's focus of like, how do you make things like run in the real world? But I think I would also agree with like you and Tom that I think this is like, for me, one of the most exciting things where it feels like magic. And I know that, for example, the team is currently working on like video. So how do you use transformers to sort of tokenize videos and model that? So I think presumably my guess is this will be like a very big direction in the future. And another aspect that I just want to mention quickly is like one of the things that you can see sort of on the OpenAI side is the application of like reinforcement learning for sort of guiding natural language generation, and also trying to align language generation with sort of human values, however you try to define that, or let's say human expected outputs. And I think that's also one area that is sort of likely to become, let's say, more mainstream as the sort of tools become a little bit more available. And Hugging Face also is doing some collaborations with researchers on that.
Great, thanks a lot.
Simon has a question.
So do you think that transformer domain adaptation will get more and more important? So I think if I understand the question correctly, you're talking about, like, let's suppose I'm trying to understand, I don't know, say COVID literature, and I've got a pre-trained model in, I don't know, Wikipedia. You know, it's never seen COVID maybe yet. So how do I adapt to that domain? If that's the question, then I think this is, in my experience, very common, and especially in industrial context, because, for example, in a previous job, I was working with a corpus that was very specific to the products of the company. So you had people asking questions about products, and if you just used like a BERT type model that was just pre-trained on Wikipedia, it sort of really didn't know, like, the context of what was talking about. So if you ask it to sort of predict the next word, it would kind of just make garbage up. And fine-tuning the language model on that domain was kind of important for getting that extra boost in performance. So I think that's one area that I think is important. And the other one that I've experienced from actually writing this book with Leandro and Tom is in the domain of question answering. So here we have a very common benchmark like Squad or Natural Questions, where models are trained on, you know, these kind of, like, let's say, artificial setups where you're given a context, a question, and an answer, and you have to sort of figure out the span of text where the answer is. And if your domain is very different, then a model that gets, you know, superhuman performance on Squad will just bomb completely on your domain. And again, doing fine-tuning and domain adaptation seems to be quite important. But if I missed the question, then please interrupt and ask again.
Thank you very much. It was more, the question was a bit also whether going larger and whether these super large models will be the future, or whether more specialized, smaller models that adapt to the domain or that include more of the world knowledge in their language model as well, whether, well, when it goes this way or the other way.
Yeah, that's a super interesting question. So one thing that I've seen in the BigScience project is actually in this direction, right? So, for example, should we just train GPT-3, like, you know, just do the same thing and just, you know, see if we can do something different? Or another very interesting approach is this idea of doing retrieval during pre-training. So I don't know if you've heard of, there are these approaches, one's called Realm or Marge. They're kind of like transformer models, but they integrate kind of retriever that basically selects, like, during pre-training, relevant passages according to some sort of subtask. So if you look at how, like, GPT-3 is able to do things like few-shot learning and so on, it's because inside the corpus, you've got lots of examples of, like, a task, like, you know, someone summarize this thing for me, and then there's a summary. And so it kind of learns these patterns. And the question is whether you can kind of engineer those patterns kind of explicitly through some sort of retrieval way. And I think the jury's out on which one of these ways go, because obviously if you do retrieval, you integrate world knowledge, because you're able to sort of explicitly say, you know, if it's Wikipedia, I'm going to explicitly tell the model, hey, this particular sort of, let's say, context is related to this other concept in the corpus, but I don't think the answer is clear. So I'm going to just have to be vague and say, don't know.
Thanks a lot.
I think you're muted, Manfred.
Are there any more questions? Well, if not, I thank you very much for that interesting talk, Luis, and
Thanks for having me.
to all the audience, have a good night and see you tomorrow.